So the idea is that if you say that's 3 jets, and now we analyze this bunch of real hadrons to try to make jets out of it, I should get almost the same jets for adding up all the red ones as I got from that one red one that was, say, at the beginning of my final diagram. So that's one way of saying the physical meaning. Another way to say it is if you simulate all this with a Monte Carlo simulation, which I'll talk about in the next talk, then that Monte Carlo simulation has a hadronization model and an underlying event model from other parton collisions. All that stuff, hadronization, I don't really know. I have a model for it, but I don't really know it very well. And if I use an infrared safe jet definition, then the effect of the hadronization model should be very small on the predicted cross-section. Okay, so I can now talk about jet definitions. There's 2 kinds. Cone algorithms and successive combination algorithms. Both of those kinds can be infrared safe. Cone algorithm was in the past a Fermi-lab more used for hadron-hadron collisions. And actually the algorithm used at Fermi-lab tended to be not infrared safe, but maybe not. It was not too badly infrared unsafe. But it can be perfectly infrared safe. And then there's this other kind of algorithm, the successive combination algorithm. And those could certainly be infrared safe. So I'm going to discuss just one of those, because otherwise it would take too long. So I'm going to discuss the successive combination kind of algorithm. And those trace back to the Jade collaboration at Daisy in the 1980s. So what do I do? The idea is I'm going to, one, choose a parameter. So this algorithm depends on one parameter, usually called R. And I'm going to start with a list of protojets, meaning what you start with, or a jet that isn't finished. And each protojet has a momentum, P, mu, and J labels which protojet it is. So I drew a little picture here. A protojet is, if you think of this thing as a tree, the protojets are the final branches of the leaves on the tree. So this one is one of them, that one's another one, that one's another one, that one's another one. And over here I got some red ones, this one and that one. Those are all the protojets I start with. And then what I'm going to do is put them all together to make jets. So I'm going to wind up with a bunch of jets. That's indicated by this line, that line, that line. The ones that come out of the green grassy area there. Okay, a lot of the jets I finally end up with are going to have quite low transverse momentum, and you don't need to pay any attention to them. You just ignore them. It's the very high transverse momentum jets that are important. Okay, so that's the background. Now let's see how this algorithm works. So it's a little computer program. But look at this. This is a computer program I can write on one page. So it's not a very complicated one. For each pair of protojets, I define a distance between them, dij. And how do I make that distance? It's the minimum of transverse momentum of parton I, or protojet I, and transverse momentum of protojet J, transverse to the beam axis. And I squared those transverse momentum. And then that's times the difference of rapidity squared plus the difference of azimuthal angle squared. And that's then divided by r squared. Okay, that's the distance measured between 2 protojets. And each protojet also has its own just individual distance measure, just that its transverse momentum squared. Okay, so now what I'm going to do is I look through all my distances, dij and di's, and I find the smallest one and call that d min. If the d min is one of the dij's, then I merge protojets I and protojets j into a new protojet, which we may call k. There's different ways to do it, but I can just say pk at the formal momentum is pi plus pj. And if the d min is one of the di's, then I say protojet I is no longer mergeable, and I declare it to be a final finished jet. Take it out of the list of things that might get merged. Okay, so going through those steps, I reduce the number of protojets by 1. And if there's any protojets left, I just circle through that and go back up to the first step. Okay, as computer programs go, that's marvelously simple. Here's just an example, supposing it's in one dimension. So transverse momenta and eta, and suppose I've got 5 protojets like that. Then what's this going to do? It's going to say, those two over there have a small distance between them, so I just merge them, and I get one new protojet with bigger momenta equal to the sum of them. And these two are close together, and I merge them, and I get that momentum. And this one's too far from anything, and it doesn't get merged. And now, given what R is, I'm not going to be able to merge any of those, so I've got 3 jets. Okay, that should be pretty simple. Is that infrared safe? You should think about that. Suppose one of the protojet momenta becomes 0. Then when it merges with another protojet, really nothing happens. If pj is really, really small, this pi plus pj is just about pi. So infrared protojets don't matter. And if 2 protojets become parallel, so pi is something times pj, then if they're very parallel, they're merged right away. And pk is then pi plus pj. So it wouldn't have mattered if you had, right from the beginning, replaced protojets I and j by protojet k with the sum of the momentum. Okay, so it's just infrared safe. And this is called the KT jet algorithm. Why KT? That might seem like a kind of mysterious name. It's because this quantity here, transverse momentum squared times angle difference squared, is essentially the transverse momenta of one of the protojets relative to the sum of the mother protojet, that when you put them together. Transverse momentum relative to the direction of their common direction, and divided by r squared. So it's because this is like a transverse momentum that is called the KT jet algorithm. Here I've got a little picture of what KT is. Here's one of the momenta. Here's the sum of them. That's the KT. And now there's a little clue here. Why did we have this R factor? What is R doing? So suppose that PTI is less than PTJ. I mean, one of them has got to be the smaller, but I be the one that's the smallest. Then think about putting protojet I together with protojet J. So here's what Dij is here. Here's what Di is. So this minimum of PTI and PTJ is PTI squared. So PTI squared is common to those. So Dij is the smaller one if this angle difference squared is less than r squared. That is to say, I put protojets together if their angular separation is less than this r squared. And r squared is an adjustable boundary, something of order 1. It's often chosen to be 0.7, 0.5, 0.4. In fact, there's a little bit of embarrassment that Atlas and CMS can't agree as to whether it's 0.5 or 0.4. So one uses one and the other uses the other. Anyway, protojet I is not mergeable with protojet J if Di is less than Dij, which means that the angle distance is bigger than r squared. So why is that in the definition? is because if you've got, what's on the next slide? Oh, finally, a lot of protojets. What's going to happen in a real event is there might be a jet that you're interested in. That's this area here with lots and lots of transverse momentum. And then some other particles coming on with only 1 GeV of transverse momentum. It's all around here. Well, the algorithm is going to form those into little jets. But the whole calorimeter is filled with those little jets. They come from initial state radiation, they come from the underlying event. You don't want them to be part of your big jet. So this protojet will not get merged into that important protojet if the center of that important protojet is bigger than distance r from the one that you didn't want. So if you make r big, it's sucking more stuff into the jet. And if you make r small, it's leaving a lot of stuff out. That's the idea of it. Okay? Here's just a picture that I think is rather nice. It's from a paper of Kachari, Salon, and Soyas. They just took a sample event and made a Lego plot of it and grouped it into jets with a KT jet algorithm. And then they put in a lot of little teeny cells all over the place, everywhere, but only with 1 electron volt of transverse momentum in each little cell, just to see where those cells would go. Which jet would they belong to? So what you see is, let's say, there is a jet there with a spike in it. Here's another one, a green one. Everything in this region gets associated to the purple jet. Everything in this region gets associated to the green jet. And what you can see from that is that the area soaked up by any one of these KT jets is kind of irregular. They don't overlap. I mean, every cell is either in one jet or the other one. But the shape is, they're not circles. They're sort of strange. Okay, so that's what happens with the KT algorithm. There's a couple more algorithms, but the ones I'm going to show you are all in the same style. So there's something called the Cambridge-Aachen algorithm, and you'll frequently see, if you go to any talk about jet substructure, you're likely to see something about Cambridge-Aachen algorithm. What you do is same style, but now the Dij is the angle difference squared divided by r squared, but no pt squared. And the di is just 1. So if you put things together with a Cambridge-Aachen algorithm, only angles between protojets count. The transverse momentum in the protojets don't count. Well, you might think that's nice. It's certainly simple. And here's a picture, it's the same event that we had before, but now made into jets with the Cambridge-Aachen algorithm. You get different jets, more or less the same, but somewhat different. So here's the purple jet. I don't think you can quite see it, but there's 3 little towers inside the purple jet. It's not a very good jet. And here's the green jet. They're still irregularly shaped. Even though it's just angles that count here, the shapes come out to be rather irregular. Okay, and then there's one more I'm going to show you. That's called the anti-KT algorithm. And that's a variation on the same successive combination plan. But now the Dij is the minimum of 1 over PTI squared, or 1 over PTJ squared, and then times the same angular distance. And the Di is 1 over PTI squared. So instead of having here, in the KT algorithm it was PT squared, now it's 1 over PT squared. That's why it's opposite from the KT algorithm. Everything else in the algorithm is the same. Okay, that's a possibility. It's still all right, it's infrared safe. It's not anything anyone would have thought of until it was thought of. You may think that what a jet algorithm is doing is putting things together, starting at this end, according to the way they would have been made in a part-time shower, say in the Feynman diagrams. So, one mother part-time divides into two part-times, and that divides into two more, etc. The KT algorithm has a chance to put things together in the way they were made. There's no definite way that a given bunch of protojets would have been made. If you ran Pythia to do it, Pythia would sometimes make it one way, sometimes make it another way. But at least the KT algorithm is a plausible way. Here, this is completely implausible with the 1 over PT squared. That's not the way the showers work. It's not the way QCD works. Nevertheless, the anti-KT algorithm is quite popular, and jet cross-sections are getting reported with the anti-KT algorithm. And here's why. Here's a picture of how jets get made with the anti-KT algorithm. So now this was a very high transverse momentum thing just in one cell. And so 1 over PTI, this one is I, 1 over PTI squared is enormous. I'm sorry, 1 PTI is enormous, 1 over PTI squared is small. So this very high PT cell wants to pick up everything that's within R of it. So it picks up everything in this nice green thing, and that's a circle. And this red one is the next highest PT thing, and it picks up a circular region around it. At the cost of, well, the green one picked up everything inside of a circle in 8 and 5 space, at a cost of the purple jet, which now lost a big chunk of it. It's as if the green jet just ate a part of the purple jet. So in this way, the highest PT jets have everything that's inside a beautiful circular region. And for that reason, the anti-KT algorithm is pretty much popular. Okay, so that's what I have to say. I've got a couple of conclusions, and I'm going to go on next time to talk about part-time showers and factorization. And right there, after part-time distribution functions. But so far we've found out about jets. QCD gives us jets, right straight from the theory, and in a very simple way. And those jets are seen in experiments. And then to measure a jet cross-section, you've got to be precise, so you need a definition of a jet. The definition needs to be infrared safe, so what I've shown you is a few infrared safe jet algorithms. And they typically use an angular size parameter, usually called R. So when you hear some talk where somebody's measuring a jet cross-section, or they're measuring cross-section for W plus 3 jets, whatever, they've got a jet algorithm in there, and they will tell you what their R is, and now you know what it all means. And the conceptually simplest kind of definition is these ones that successively combine small protojets together into bigger and bigger ones until you can't combine anymore, and then you just say you're done, and you take the highest transverse momentum jets that you found. Okay, thanks.
Good questions? Yes, go ahead.
So, which infrared safe algorithm should I use to compare with theory?
Well, any of them.
But they may not give the same answer because they define jets slightly differently.
Yes, but there's no best answer, I think. Personally, I prefer the KT algorithm, but you can use the anti-KT algorithm. I think the successive combination algorithms, to my mind, are nicer than the cone algorithms. I don't know that they're more accurate in any sense.
But in some sense, if it doesn't agree with theory, one can always blame it on either the wrong theory or the wrong combination. So suppose I get to very precise measurement, so forth. Okay, so there is no definite answer.
As to which one is best, well, there's a little bit of an answer, and I can tell you that. But really, supposing, I don't want to go back through all the slides, but you remember, data compared to theory for jet cross-section, it agreed beautifully. What if it didn't agree?
Right, like what?
Then we would be in trouble, and we would look very hard for physics beyond the standard model.
But does it have to be, or can it not just be
Well,
the wrong combination?
yeah, so does it have to be? So now, when you find a disagreement between theory and experiment, you need to figure out what's going on. So first of all, you need to look at the experimental errors. Okay, so we were just seeing, or this morning, we were seeing different experiments that disagreed with each other. One of them is wrong, I guess. And we need to carefully analyze the experimental errors that go into that. And so it's a mystery to me, but maybe somebody knows. Yes?
Well, there's some way to define the size of R.
The size of R, okay, so let me hold that in my mind for just a second. So we're talking about the experimental errors. So let's say that the experimental errors are sufficiently small. Then we need to talk about theory errors. Because so far jet cross-section comes in next to leading order theory, not next to leading order, much less next to the fourth to leading order. So it's not exact. And if we do it to next to leading order, there's terms that I've neglected that are of order, relative order, alpha strong squared. And we don't know what's the coefficient of alpha strong squared, but you can estimate it. And the usual way to estimate that is by varying the scale, say of alpha strong of Q. Well, Q, you could make it 2Q or half Q. And there's part-time distribution functions in this that have a scale, and you could change that scale. So that's a way of estimating the errors. And if I make R too small, the errors will get bigger. If I make R too big, the errors will get bigger also for different reasons. So I can adjust the R to get a fairly small error. And by the way, if I got a different error estimate for different jet definitions, I would like to choose the jet definition that gave me a reasonably small error. However, to my knowledge, I get about the same size of error for any of those jet definitions. So I don't think it really matters.
But is there any sort of systematic error between different jet definitions?
Well, the only thing you can do is
Right.
try the method I mentioned to estimate the error, given anti-KT, given KT, whatever, and see if one of them is 5 times the other.
Do they do that experimentally?
Yes, I think so, and I don't think there's a difference. I must say I haven't looked at the literature on it, but I don't think there's any substantial difference.
All right. No, okay.
Okay. You mentioned that a irregular shape for like KD errors. So I think that this irregularity may come from the soft rule. Right? So because you compare soft rule first, so the J shape looks irregular. But if we can weight each particle by energy, by its energy, then say for example we plot the energy distribution within the jet, then the shape may look more like a round shape. So if we can, I think it partially answers Professor C.S. Lam's question. So if we can define an observable which is sensitive to these soft rules, like energy profile, then it doesn't make then I think the comparison with the theory will be more. Because that.
Well, that's an interesting point. So what you're mentioning is jet substructure. One simple jet substructure measurement is how is the energy inside of a jet distributed as a function of the distance away from the center. And for different jet definitions, you're going to get a different distribution. And I'm not sure how different, but they've got to be somewhat different.
Well, okay, so I think the time's up.